this is John Whitaker for the Mathematical Analysis 1 class, and this is our 16th video lecture. And last time we ended up with a theorem, we ended on a theorem having to do with looking at a sequence of intervals in R1, and such that one of them was contained in another one, contained in the next one, and so forth in terms of our sequence. And what we had said was, well, if that's the case, that the intersection of those intervals will be non-empty. Today we're going to start off by extending that result to K-cells. So here's what we have. We're going to let K be a positive integer. If I sub n runs from 1 to infinity, is a sequence of K-cells such that I sub n plus 1 is contained in I sub n. We say that they're nested in this sense. Then the intersection as n runs from 1 to infinity of I sub n is non-empty. And this is just extending the theorem that we ended with from R1 to RK. Okay, so the proof is we let IN consist of all points that have the form x bar, okay, equal to, so it's a k tuple, so it's x1, x2, all the way up to xk, such that for each coordinate we have some bound. So a sub n comma j will be less than or equal to x sub j, which will be less than or equal to b sub n comma j. So these are the a sub j's and the b sub j's that are the endpoints for that particular coordinates. And I wrote down n because it corresponds to I sub n. We have, n's running from 1 to infinity. Okay, that's what we have. And as a matter of fact, let me add this comment. This is true for for 1 less than or equal to j less than or equal to k, and n element of the natural numbers. All right. Okay, so what we're going to do is we're going to let I sub n sub j be equal to just the interval in R that is a sub n comma j up to b sub n comma j. So that's integral in R1. And we're going to do that. We can notice that for each j element from 1 up to k, we have that I sub n plus 1 comma j will be contained in I sub n comma j, and that's true because in general we have this I sub n plus 1 is contained in I sub n. So because in the k-space this happens, it's going to make it happen on the each individual coordinate space. Since these are just in R by the previous theorem, the intersections of the I sub n, this was a little j here, make this a little j, I sub nj, as n runs from 1, so this is for any fixed j, to infinity, is non-empty. So that means for each j element from 1, 2, up to k, what we have, so for each one of them, we've got an x sub j, if you will, coordinate. There exists, and I'll write down x sub j star, so this is just a real number, it's a coordinate, such that a sub n comma j is less than or equal to x sub j star is less than or equal to b sub n comma j. Okay. So, and this is true for all n. Element of the natural numbers. That's what happens. So, if we look at the corresponding point in x sub k, we call it x bar star, which equals to x1 star, x sub 2 star, all the way up to x sub k star. Okay. Then this will be equal to, this will be an element of in for all n element of natural numbers. Okay. So that means that x star bar is an element of the intersection, is n runs from 1 to infinity, of the I sub n's. Thus, the I sub n's are non-empty. That concludes that proof. I have room to write down the next theorem. And here's what it is. It says every k-cell is compact. So remember, this was k-cell was something that was in Rk, and really what it was points in Rk. It consists of each coordinate being in a specific given closed interval in R1 for each coordinate. So let's see if we can prove this. When I get this proof done, this theorem is true for any K cell. So let me back up. This theorem is true for any K cell. So in particular, it's true when K is equal to 1. So it's saying that any interval A to B closed containing those intervals are going to be compact. Okay? And when I was talking about compact sets, one of the examples I gave was 0 to 50 closed was compact. And this theorem is what's telling us that it's going to be compact. It's a long theorem, a long proof, okay? And it's by contradiction. So it says, we start off by letting I be a K cell. Consisting of points of all points. X bar equal to x1, x2, up to xk. And where each coordinate has to satisfy being in between some numbers. So aj is less than or equal to xj is less than or equal to bj, b sub j. For all 1 less than or equal to j less than or equal to k. So for all the coordinates. Now these, a sub j is different than b sub j, and a sub 1 is different possibly from a sub 2 and so forth. Okay? So we're trying to show that this I is compact. So what we're going to do is suppose, we're trying to do this by contradiction, there exists an open cover of I, say, collection of G sub alphas, alpha is element of A, such that there is not a finite subcover of I from this collection of G sub alphas. It doesn't have a finite subcover. What we're going to do is we're going to break up each coordinate's interval, okay, that makes up I, in half, if you will, okay, into two parts. Okay, and how we're going to do that is we're going to put C sub j equal to A sub j plus B sub j over 2. So then if we look at the intervals, A sub j up to C sub j, and C sub j up to B sub j, okay, they determine two K number of K cells, okay, and I'm going to call them Q sub I, where I would run from Q sub I, where I would run from 1 up to 2K, whose union such that the union of the Q sub i's equal to I. Okay, look, this seems a little confusing here, maybe. But what I'd like to look at for a second is, I'm not going to concentrate on because it's really not part of the proof. It's just for us to get an understanding of this lines. But if you look at a cube, if you will, in R3, okay? So that's R3. Really, if you look at a corner of the room, okay, or if you look at a tabletop, and what I'm going to do is the cube I'm going to look at, this is going to be my eye, so it's in R3. It's the cube who comes out 2 units, goes down 2 units. I'm not going to be able to draw this very well. Matter of fact, it looks terrible. Okay? But I think of it on the table, and I want to have 2 units. If you think of a corner of a table, think of a cube. You're at the corner of the table, maybe at the right corner of the table's in front of you. Okay? And you're at the right corner of it. And what you do is you think of this cube being 2 feet high, 2 feet in front of you, and 2 feet to the left of you if you're right at the corner of the table. Okay? And what we're going to do is break that cube into, because we're talking about being a cube in R3, okay, into 8 parts, 2 to the 3rd parts. And that cube is going to be broken up into a cube, 8 cubes that have, if you will, a volume of 1. But what we're going to do is, along that table here, to the left, you go 1 unit, and then 1 more unit, and that completes the cube, if you will, that we originally started with. Cut the moving left in half, if you will. We'll cut the cube moving forward in half, so it was 2 units moving forward, if you will, 2 feet. You could say first feet, then the second feet. And then we'll only talk about those cubes, those subcubes, if you will, being only 1 foot high, where the original cube is 2 feet high. So that bottom layer is going to have 4 cubes in it, if you will. And then on top of it, we're going to have 4 cubes. And that's how we're going to get 8 cubes, or 2 to the 3rd, where we're talking about in R3, we have an X coordinate, Y coordinate, and a Z coordinate. Okay? So that's what we do. If you union up those cubes, you're going to get I. That's the way to explain, one way to look at it. It's an example. Okay, so we get I. Okay, now the thing to notice is that since I is not compact, what has to happen is that at least one of the q sub i's is not compact. But if they were all compact, okay, then what you would do is you would just take the finite ones that cover q sub 1, the finite ones that cover q sub 2, all the way up to the finite number of open sets from g sub alpha that cover q sub 2 to the k. You take all those finite ones and you add them together, you're still going to get a finite number, and that would cover I. So at least one of them can't be compact. Okay? Now let's call it I sub 1. Okay? Let's just call it I sub 1. Okay. So it's a lot smaller cube or K cell than what we had started with. Okay? Okay. That's what we're going to do. Okay. And what I'm going to just continue on here, so for I sub 1. And so Q sub, or I sub 1 is not compact, if you will, so it is not covered. Cannot be covered by a finite subcovering of the G sub alphas that we're working with. Okay. We then subdivide I sub 1. It's in it's a K cell, and find and I sub 2 by the same process. Okay, so we end up with, we take I sub 1, it has K coordinates, which are, each coordinate has a range for which the coordinates come from. You take half of them. Anyway, you do the same process. So we have finally obtained a sequence. Let's call them I sub n. And they're going to satisfy certain properties. And here's two of them that I'll write down with the following properties. The first one is that I sub n plus 1 will be contained in I sub n. That's true for all n element of natural numbers. And I sub 1 is going to be contained in I itself. 2, the second thing, let's call it A. The second thing, B, is that I sub n is not covered by any finite subcollection of G alphas. There's a third characteristic that these sequences of I sub n will have, but I need to do a little work first. To get this third important characteristic. Okay. And so, first of all, let's go back. Let's recall, okay, that I itself consisted of points x equaling to x1, x2, up to xk, okay, such that a sub j is less than or equal to x sub j is less than or equal to some b sub j. So a sub j and b sub j are real numbers. Now what we're going to do is we look at this delta. It's going to be a positive number. And you look at it as the sum as j runs from 1 to k of b sub j minus a sub j. So for each coordinate defining interval for this k cell I, we look at the distance between the endpoints for the j coordinate, okay? We take that distance, we square it, okay? And then we add all those up, and we take half of that. So we'll look at that. Then what we notice is the following. If we take x that's an element of I. And, y being an element of I. So you take any two guys that are in I. Then, if you look at their distance, okay, with the usual metric, that's their norm, x minus y. And you square that. If you look at their distance squared, that's going to be equal to the sum. Okay, so how do we do this? If you take their coordinates, they run from 1 to k. X sub j minus y sub j, okay, their coordinates. You have to square them. Okay, that's what it is. And then the norm would be the square root of that, but we're squaring it, so that's what we have. But that distance is going to be less than or equal to, each one of these distances less than the b sub j minus a sub j. So this sum will be less than that sum. Okay? So what we get is that the distance, if you will, not the square, but is going to be less than or equal to this. So we're taking the square root of both sides of this inequality, so it's going to preserve this inequality. Okay. So that's what we have. And that's equal to delta. Okay. All right, so for our sequence, I sub n, we're going to get a third characteristic. Note our sequence I sub n will also satisfy this third quality, and that is if x is an element of I sub n and y is an element of I sub n, then the distance between x and y will be less than or equal to 2 to the minus n delta. All right. I want to go back, look at this just for a second. Where is this coming from? You know, this quantity right here was working with I itself. And so what you're doing is if you were working with I sub 1, you'd be taking half of this, because you'd be working, you know, we had split up these intervals in half, if you will, so you'd be half of this. And then you might say, well, the k's going to take, but the 1/2 that would be just involved with each one of these terms for j doesn't depend on j, it's just 1/2 every time. And so it can be pulled out, you would have the square of it, really. It'd be 1/2, and that would be squared as well. But then you take the square root, and you just get 1/2, and it can be pulled out. Okay, so you pull it out, it's being squared, take the square root, just get 1/2. And it doesn't depend on k, so it's 1/2 every time for I1, you know, for each one of these terms. It's a constant involved in this sum. And if you did it for the I sub 2, it would be 1/2 of what you just did. So that's 1/4, and that's 1/2 raised to the second. And so I sub n, you're going to have 1/2 raised to the n involved in this sum. So that's what we have. That's what we get this result. Okay, now, by 1, which was the containment, and the previous theorem, okay, there exists, so remember that previous theorem was these i's, these k cells that they're contained one inside another, then their intersection is non-empty. So there exists an x star bar, I'll say, x sub star bar, which is in every I sub n. Okay? Now, for some alpha element of A, what we're going to have is that this x sub star bar will be an element of G sub alpha. Okay? So the collections of G sub alpha will cover, any IN, okay? And so x sub star bar has got to be in one of them, one of the G sub alphas. Okay, and what do we know about these G sub alphas? Well, they're part of an open covering. This particular G sub alpha is part of an open covering, and it's open. Okay. So let's talk about what we can get from G sub alpha being open. Okay? Then that means this x star bar is an interior point. So there exists an r greater than 0 such that if y bar minus x sub star bar is less than r, then y bar is an element of G alpha. Okay. So, we pick n so large that this quantity, 2 to the minus n delta times delta, is less than r. Now, we let y be an element of In. Okay. Then y is an element of G sub alpha. Okay. And so what that gives us is I sub n is going to be contained in G sub alpha. And that's a contradiction the second thing, that no finite subcover of the collection of G sub alpha can cover I sub n, any one of them, but I've got them all in G sub alpha. Okay. And that concludes that proof. Okay. Let's move on to another theorem that states that three things are equivalent. Here's that theorem. If a set E in Rk has one of the following properties. It has the other two. The other two properties. And so here are the properties. A, E is closed and bounded. B is, E is compact. And C is every infinite subset of E has a limit point in E. Okay, how do we show these three things are equivalent? Well, we have to show that if you have one, you'll have the next one, and so forth. So we make a loop that if A is true, that's going to force B to be true. And if B is true, that forces C to be true. And if C is true, that forces A to be true. So here's the proof. Well, first we'll always show that if you have A, that implies that you have B. So we suppose E is closed and bounded. We want to show E is compact. Okay, so we haven't used this definition of bounded very much, but since E is bounded, what's that mean? That means there exists a positive number m and a point q in E. Okay? Not in E, but rather in, not in E, but rather in our case, such that the distance between P and Q will be less than m, and that's true for all P element of E. You know, we'll just call them Q's without the bars. That is, there exists, okay, so this Q is really a K tuple. Q sub 1, Q sub 2, up to Q sub K, element of RK, and m greater than 0, such that for every P element of E, the distance, okay, well, let's give P a representation. You know, it's P sub 1, P sub 2, up to P sub K. So we won't talk about the distance being less than m. And so here's what we have, writing that out explicitly. The usual metric here is the difference of Q and P in the norm. Okay. That means that the norm is the sum of the PI minus the QI, as I runs from 1 to k, that's squared, and you take half of it, and that's going to be less than m. Okay. So what that says, that's for all I that's an element of 1, 2, all the way up to k. So let's just look at these parts itself. Look, these are non-negative numbers because we're squaring them. The square of them are non-negative numbers. So we're adding up a bunch of non-negative numbers by taking the square roots of them. So here's what we can say is that for all of these individual differences, when we square them, if you take the square root of them, that's going to be less than take the square of both sides. That's m squared. And we're going to take the square root of that. So here, imagine taking this and squaring both sides, okay? So we would just have, without this 1/2 power, this squared, okay? Now this sum is less than this guy squared without this, okay? And so each individual part that we're adding up, since they're positive, has to be less than this guy squared. And so the square roots of each one of them are going to be less than the square root of m squared, which is what I'm writing here. Okay? Now, this says that the absolute value of pi minus qi absolute value is going to be less than the absolute value of m, which is just m. So, what we get is, here this would say that minus m will be less than pi minus qi, which would be less than m. Okay? This is true for all I. And so, remember the q though, when it's fixed, minus m plus qi is going to be less than pi, which is going to be less than m plus qi. This is true for all I. This statement goes with the statement about absolute values. Okay? So what does it mean for something inside absolute values to be less than a positive number? It's in between that positive number and its negative. That's what it means, and that's what I've written here. And then we just added qi to both sides. So this gives us, okay, well, one thing smaller, I'm sorry, let me back up for a second. One thing smaller than minus m plus qi, qi is a real number, is minus m minus the absolute value of qi. That's one thing smaller. And the same thing for the other side, in terms of replacing qi with the absolute value of qi. That's going to be bigger. So what we have is that minus m minus the absolute value of qi is going to be less than pi, p sub I, which is going to be less than m plus the absolute value of q sub I. Thus, P is an element of I where I is a Q cell, or it's a K cell, I should say, defined by I equal to the set of all x's in RK such that minus m minus absolute value of qi, that's going to be a fixed number because q is fixed,
is less than, let's say, x sub I, which is less than m plus absolute value q sub I. So it should be less than or equal to here every time. Okay? So that's what it is. Thus, E is a subset of I. Okay, so E is some closed bounded set, we have that's in I. So since E is closed, and I is a K cell, then I is compact. And what we've shown is that every closed subset of a compact set, we've shown that that is compact. So I say, and by a previous theorem, E is compact. And that's showing that A implies B. Now we want to show B implies C. Okay. So what are we trying to do? We're trying to show that we're assuming that E is compact. What we want to show is that every infinite subset of E contains a limit point of E. But that's something we've already shown. We have previously shown has a limit in E. Okay, that's something we've already shown. So now what we have to do is we have to show that C implies A. And that is lengthy. So we will leave that till next time, and we will cut off our lecture at this point. And so we'll start next time with that C implies A. Thank you very much.